Hi there, I'm Surajit and you are welcome to our YouTube channel. And in last few classes, we have talked about different type of coordinate system. We started with rectangular coordinate system. Then we have also talked about 2D polar coordinate system, spherical polar coordinate system. And at the end, we have discussed about cylindrical coordinate system. So in this video, we'll talk about gradient, curl, and divergence. So mainly we will learn how to write gradient, curl, divergence in different coordinate system and what is their physical meaning. Okay. So we'll start with the gradient and then we'll talk about divergence and curl. Okay. So let's start with the gradient. So mainly we'll discuss the gradient of a scalar function. So right here, gradient of a scalar function. Gradient of a scalar function. Okay, let's consider a certain region. It's a certain region R, and in this region, consider a scalar function phi, which is function of x, y, z. So what? So let me just write the definitions of gradient first, and then we'll try to understand what is the physical meaning of gradient of a scalar function. So right here, if phi, which is function of x, y, z, represent a scalar function, represent any arbitrary scalar function, any arbitrary scalar function, and it is differentiable at each point in a region R, then gradient of the scalar function phi is defined as grad of phi. How will you do this? Grad of phi, and how it is defined? It's defined in this way. So to define a gradation of a scalar function, first we have to take the derivative of phi with respect to x, then we'll multiply with I cap, plus we'll take partial derivative of phi with respect to y, then we multiply with j cap, plus we'll take partial derivative of phi with respect to z, and then we'll multiply with k cap. So this is the way how we can define a gradient of a scalar function in rectangular coordinate system. When the scalar function is function of x, y, z, then we will use this definition. We'll use this definition. We will write this gradient in scalar function, and we can define the gradient of the scalar function in this way. So as you can see here, when we take the gradient of a scalar function, it represents a vector quantity. Vector quantity. So now we know how to write this gradient of a scalar function in rectangular coordinate system. Then the next we have to learn that what is the physical meaning, what is the physical meaning of this grad of phi. So when we take a gradient of a scalar function, we have to understand what does it represent. So right here, what we have to know now, or what is our question now? What does it represent? Does it represent? So when we take gradient of a scalar function, now we have to understand what does it represent. So first of all, when we take a gradient of a scalar function, it gives a vector quantity, and that vector quantity is always perpendicular to the level surface phi. Level surface of any scalar function phi. So let me write this statement first here. Grad phi represent a vector quantity which is perpendicular to the level surface of the scalar function phi. Okay. So if we have a scalar function of phi, then if we take the gradient of this scalar function phi, that will give a vector quantity which will be perpendicular to that level surface. Okay. So we can also understand this statement by doing few steps of mathematics. For that, let's consider this is a coordinate system, let's say x, y, z, and then we have this is a level surface of some scalar function phi. So what is level surface? Level surface is a surface on which the value of scalar function is fixed everywhere. So if this is representative of scalar function phi, then the value of phi on this surface at every point must be same. So we can write phi is equals to constant. Phi is equals to constant. So on this surface phi is constant. Everywhere phi is constant. So this type of surface is called level surface. So this is the level surface of scalar function phi. So now what we are going to do here, we want to prove this statement, whatever we have written here. We have written here that if we take the gradient of a scalar function phi, that will be always perpendicular to the level surface phi. We have to prove this statement. Yeah. So prove this statement. In order to prove this statement, what we have considered here, we have considered rectangular coordinate system, and here also we have drawn a level surface of scalar function phi. That's mean phi supposed to be constant over the surface. And now we consider we are assuming 2 point. Let's say 1 point is P, and it has coordinate, let's say x, y, and z. And also we are considering another nearby point to this P. It's very nearby point, but just to represent here so that we can understand, I am taking this point here, but you have to understand that these 2 points are very nearby, very nearby to each other. So this Q point has coordinate x plus dx, y plus dy, and z plus dz. Okay, so far what we have considered a level surface of phi, and on this level surface we have considered 2 points P and Q. P point has coordinate x, y, z, and Q point has coordinate x plus dx, y plus dy, and z plus dz. Okay, so let me write first here. So assume two nearby point P has coordinate x, y, z, and Q it has coordinate x plus dx, y plus dy, and z plus dz, where on a level surface of an arbitrary scalar function phi. Scalar function phi, which is function of x, y, z. Okay, so we have considered a level surface of scalar function, an arbitrary scalar function, and then on this level surface we have considered 2 point P and Q. So now what I am going to write here, let's say first we have measured the value of the scalar function at point P, and then if we go to point Q, so if there any change in phi, how we can represent that phi, change of phi? So write this line here. If we go from point P to Q, then the change of phi can be written as, how we can write this change of phi? D phi is equals to rate of change of phi with respect to x, and then if we go from P to Q, we'll change the value of x by dx, so you have to multiply with dx. So first term represent the rate change of flux because of unit length of unit change of x, and then if we go from point P to Q, we actually change the x value by dx, we have to multiply with dx, plus same way change of y with respect to y, rate of change of y with respect to y, and then dy, and same way with z, del phi by del z, that is rate of change of phi with respect to z into dz. dz. And if we manipulate this thing, and we can write in this way, or we can represent this our plan in this way, del phi by del x I cap, del phi by del y j cap, del phi by del z k cap, dot dxi cap dyj cap and dz k cap. Okay. And the way we have defined a gradient of a scalar function, so from this definition we can say that this term represent the gradient of the scalar function phi. So we can write grad phi. So we can replace this term by grad phi, and then dot this term we can represent an elementary length vector or a vector between p and q, that is dr vector. Dr vector. Okay. So if we go from point p to q, if there are any change on phi, we can represent this change of phi by this way. But what we have assumed here, we have assumed that the p and q, they lies on the same level surface of an arbitrary scalar function phi. So if p and q both are lies on the same level surface, and according to definition of level surface, phi is supposed to be constant over this surface. That's mean if we calculate the value, if we measure the value of phi at point p, and then if we measure the value of phi at point q, both the point phi should have same value. So the change of phi must be 0. Change of phi must be 0. So let me write this argument here as p and q both lie on the same level surface, same level surface of scalar function phi. So therefore del phi must be 0. Del phi must be 0. If del phi is 0, then what we can write? We can write grad of phi dot dr, this is equals to 0. This is equals to 0. Now p and q, they are two different points, so the magnitude of dr is not equals to 0. And also if we assume that the gradient magnitude of grad phi is not equals to 0, then what we can write from here? We can write that two vector, their magnitude are not 0, but their dot product is 0. That simply suggests they are perpendicular, mutually perpendicular with each other. So in this case, grad phi will be perpendicular to the vector dr. Grad phi and dr, they will be the perpendicular with each other. Okay. So again, let me draw this figure: x-axis, y-axis, z-axis, and we have assume a level surface of scalar function phi on which scalar function is fixed. And then what we have considered? We have considered 2 point P and another nearby point, which is just nearby point to the Q, the Q point, which is just nearby point to the P. So from this figure, we can say that when we connect these two vectors, we'll get a vector quantity, length vector, which will be parallel to the surface or tangent to the surface. So in this case, we can say that dr vector is tangent to the surface. Dr vector is tangent to the surface. So right here, since dr vector is tangent to the level surface, tangent to the level surface, then what we can say, this vector is tangent to the level surface, but grad phi is perpendicular to this level surface, to the dr. So grad phi, let's say along this direction, then we can say the grad phi is perpendicular to the level surface. So therefore grad phi is perpendicular, grad phi is perpendicular to the level surface of the scalar function phi. Okay. So whatever we have written here, that we can understood from this figure. So first properties of so what we have noticed here, phi is a scalar function, but when we take the gradient of this phi, it will give us a vector quantity, and that vector quantity will be always perpendicular to the level surface and scalar function phi. So if we calculate gradient of a scalar function on the level surface of any arbitrary scalar function, then that gradient will be always perpendicular to the level surface. And then second thing, grad phi also give a direction along which the rate of change of phi is maximum, and the magnitude of grad phi give the direction, magnitude of grad phi give the maximum rate of change. So let me write the second statement here. The direction of grad phi gives the direction of maximum rate of change of phi. So grad phi is a vector quantity, and this directions of this grad phi give us the maximum rate of change of grad phi, and the magnitude of grad phi represent the maximum rate of change of phi. Maximum rate of change of phi. Okay. This is the second physical interpretation of grad phi. First interpretation, what we have noticed here, if we take the gradient of a scalar function, it will give us a vector quantity, and if the scalar function, if we take this gradient of a scalar function on level surface of any arbitrary scalar function, then that vector quantity will be always perpendicular to the level surface. And then second interpretation is here, if phi is any arbitrary scalar function, and then if we take the gradient of the scalar function, that will give the directions of maximum rate of change of phi. and the magnitude of grad phi will represent the maximum rate of change of phi. Maximum rate of change of phi. Okay, so we can also prove this one, but for that let me just draw a figure here. Let's say this is x-axis, y-axis, z-axis, and this represents some scalar function, curve of some any scalar function phi, which is function of x, y, and z. X, y, and z. Now what I am going to do here, I am considering a point on this curve of the scalar function. Let's say point is P, and also I am considering an arbitrary direction. Let's say in this direction, and these directions we can represent a u vector. U vector. So in order to prove this statement, first we have to find out the directional derivative of the scalar function at point P. What does directional derivative means? Means we want to find out the rate of change of the scalar function phi at point P along the directions of u. So right here, the rate of, so what we are going to do here, we are going to prove this statement. So right here, prove. So for that, what we are going to write here, we are going to write here the rate of change of scalar function phi at point P along the direction of u vector. U vector is some arbitrary vector. So what we are going to write here? We are going to write here the change of scalar function at this point P along the directions of u cube, means along this direction. Along this direction. So the rate of change of scalar function phi at point P along the direction of u can be written as we write it in this way: d, then at point P, comma, along the directions of vector u, and then scalar function phi is equals to, so what this term represent? This term represent the rate of change of phi at point P along the directions of u, and that is given by grad of scalar function dot the unit vector along the directions of vector u. Along the directions of vector u. So at this moment, I don't know you know this definition or not. If you, I am assuming that you know this definition of directional derivative. If you don't know, no need to worry about these things. We will upload a video series on mathematical physics. That time we'll discuss again how we can write this directional derivative of a scalar function at any point phi along the directions of an arbitrary vector. At this moment, I am assuming that you know this definition and how we can represent these things. This d and here we'll write at point P. So this P point will represent, we are going to calculate the directional derivative at this point P on the scalar function phi and along the directions of vector u, and that can be represented by grad of phi dot u, where u is the unit vector, u cap is the unit vector along the direction of u. Okay. Okay. Now, if we consider that at this point, a gradient vector, let's say, pointing along this direction, grad phi, and we are considering this u vector along this direction. So the angle between them, let's say theta, angle between them is theta. Then what will be the rate of change of phi at point P along the direction of u? So the d rate of change of phi at point P along the direction of u is equals to, we can write mod of grad phi and mod of u will give you 1, and the angle between them we have assumed that theta, so it will be mod of grad phi into cos theta. Mod of grad phi into cos theta. Okay. So now what this value, what we have written here, we have written here the change of phi along the direction of u, the rate of change of phi at point P along the direction of u. So we can consider this direction of u in any direction, any arbitrary direction. So here the directions of this vector u is variable. We can consider any direction. So at this point we can go any direction. So if this directions of u is variable, we can consider at any direction. So then we can consider the value of direction, one particular direction, that is the directions when if we consider the directions of u along the directions of grad phi, then only this rate of change will be maximum. This term will be maximum. So this term will be maximum when cos theta will be 0. Sorry, cos theta will be 1, and when cos theta will be 1, when theta equals to 0. And theta equals to 0 means, if we consider this u vector along the directions of grad phi, then only this rate of change of phi will be maximum. Then only this rate of change of phi will be maximum. So the rate of change of phi at point P will be maximum when cos theta equals to 1, that's mean theta equals to 0. Theta equals to 0. And what this suggests, if we goes along the directions of grad phi, so if we consider this u vector along the directions of grad phi, then only the rate of change of phi will be maximum. Rate of change will be maximum. So other way we can say that the directions of grad phi will give us the directions of maximum rate of change of phi. So therefore we can say that the direction of grad phi will give us the direction of maximum rate of change of phi. Rate of change of phi. And what will be the maximum rate of change of phi? And d at point P along the direction u phi, that is the rate of change of phi at point P along the direction of u will be maximum. And what will be that maximum value? When cos theta will be 0. So cos theta equals to 0 means mod of grad phi. Mod of grad phi, that is the maximum rate of change of phi is represented by mod of grad phi. Okay. So these are two physical interpretation of grad phi. First of all, grad phi will give a vector quantity, and if phi is a level surface of any scalar function, then grad phi will be perpendicular to the level surface. And second thing, if phi is represent any arbitrary function, then the directions of grad phi will give you the maximum rate of change of maximum rate of change of phi, and the magnitude of grad phi give you the maximum rate of change of phi. Okay, maximum rate of change of phi. And just come back here, not here, here. So at this point, what we have written here, the grad phi is perpendicular to the level surface. So if we want to define the unit normal to the level surface, how we can define? So we can define n cap is the unit normal to the level surface, and we can define this level surface a unit normal by this way. First, we have to take the gradient of this scalar function, and then if we divide by this magnitude of this gradient, that will give us a unit vector which will be normal to the level surface, which will give the normal to the level surface. So later we'll see, we'll solve some problem where, let's say we have a equipotential surface, and if we want to if we want to find out the directions of electric field, we'll see later that electric field will be always perpendicular to the level surface potential. So if we take the gradient of this level surface and then if we divide by its magnitude, that will give us the directions of electric field on this level surface. Okay, so these are two physical interpretation that we will use later to solve the different type of problem in electrodynamics. Mainly we'll use it electrostatics and at some point of electrodynamics also. Okay, so that is all about gradient. Then next, write the divergence of a vector field. Divergence of a vector. So first we will write the definition of this divergence. For that, again, let's say consider this is a region of R, and in this region R, consider a vector quantity A, which is function of x, y, and z. This is function of x, y, and z. So then first write the definition of this divergence of this vector quantity, and then we'll try to understand what is the physical meaning of this divergence. Okay, so right here, if a vector, which is function of x, y, z, represent a vector quantity in a region R, and it is differentiable at each point in this region, then divergence of this vector A is defined as divergence of A is equals to, so if we want to write the divergence of any vector in rectangular coordinate system, how we'll define it? First, we'll differentiate x component of this vector with respect to x, plus we'll define this y component of this vector with respect to y, plus we'll take the partial derivative of this z component of this vector with respect to z, and then have to add it all this term. This is the mathematical definition how we can write the divergence of a vector quantity in rectangular coordinate system. So if we have a function, if we have a vector quantity which is function of x, y, z in certain region R, and if this vector is differentiable at every point in this region R, then at any point in this region, if we want to define the divergence of this vector quantity, what we have to do? First, we have to take the partial differentiation of the x component of this vector with respect to y. Then we'll take the partial differentiation of y component with respect to y, and then we'll take the partial differentiation z component with respect to z, and then we added them together, and that will give us the divergence of this vector. Okay, so now once we know how to write this divergence, now we have to understand what does it represent. What does it represent? What does it represent? That is, we have to understand the physical meaning of the divergence. Physical meaning of divergence. So basically, divergence is a differential operator. Nefla, you can see here what we are doing here. We are actually differentiating this vector. So when you operate this divergence of a divergence operator in any vector, that's give actually some nature of this vector field. Nature of this vector field. So that we have to understand here. So for that, let me draw three vector quantity in xy plane. So first vector quantity, k vector is equals to, let's say, xi cap, yj cap, and then second vector b vector equals to minus xi cap minus minus yj cap, and let's say third vector c I cap plus j cap. Okay, I cap plus j cap. So now what we are going to do here, we are trying to draw this vector field in xy plane. Let's say this is x-axis, sorry, this is y-axis and this is x-axis. This is also y-axis and this is x-axis. This is x and this is y. Okay, so when we represent a vector, on any plane, what we actually represent an arrow. The length of this arrow will be proportional to the magnitude of this vector, and the directions of arrow give the directions of this vector quantity at that point. Okay. So if we want to this vector in xy plane, we can draw like this way. When at origin x and y both are 0, so it will give you a null vector. And then let's try to draw the vector quantity on the x-axis. Let's say at this point when x equals to 1. So on the x-axis y will be 0 and x will be 1, 2, 3, 4. So when x equals to 1, the length of this vector will be 1 I cap. So this. And then when x equals to 2, that will give you 2 I cap. And when x equals to 3, that will give you 3 I cap. Yes. And same way on the negative x-axis, we can draw like this way. Minus I cap, minus 2 I cap, and then minus 3 I cap. And same way on positive y-axis, x will be 0. And you put y equals to 1, that will give you 1 j cap. You put 2, 2 j cap. If you put 3, then it will give you 3 j cap. And on the negative y-axis, it will be minus j cap, minus 2 j cap, minus 3 j cap. And in between the xy plane, let's say consider a point 1, 1. So at this point, this vector quantity will be I cap, j cap. So it will be along this direction. And then if we put 2, 2, again it will be in this direction, but magnitude will be 2 times of this vector. And then if we put 3, 3, it will be like this. And same way, if we put x equals to minus 1, y equals to plus 1, then this vector will be along this direction. And then minus 2 plus 2 and minus 3 plus 3 will give you same. And if you take the x equals to minus 1, y equals to minus 1, this will be along this direction. And then minus 2 minus 2 will be this, and minus 3 will be this. Same way, if we take x equals to plus 1, y equals to minus 1, will be along this direction. Then x equals to plus 2, y equals to minus 2, will be along this direction. And this direction. When I put x equals to 3 minus x equals to 3 and y equals to minus 3, vector will be like this. Okay. So if we draw this vector, schematically this vector field will look like this. And on the other hand, if we represent this b vector, it will be almost same, only the arrow will be different because it's a negative opposite to this a vector. So we can simply write like this. Yeah, like this. And then this point, at this point, And then if we want to represent this third vector, I cap, j cap, I cap plus j cap, so everywhere it's independent of x and y, so everywhere whatever we'll put the value of magnitude will be under root 2, and direction make 45 degree with the x-axis and y-axis. So we can represent this way. Everywhere magnitude will be same and directions will also be same. So this we can represent like this. So we have considered a 3 vector and we have drawn the vector field associated with each vector in the xy plane. Now what we have to do, we know the definition of the divergence of vector in rectangular coordinate system. So according to this definition, we want to calculate the divergence of this vector quantity. Okay. So if we calculate the divergence of the first vector quantity, what we'll get? We'll get divergence of A. How we have defined this divergence? First, we have to differentiate the x component with respect to x, and then y, and then z. And we have to add all these things together. So in this case, for a vector, x component is x and y component is y and z component is 0. So when we differentiate this x with respect to x, that will give you 1. Plus when you differentiate this y with respect to y, that will give you also 1. So it will give you 2. 2 means it's a positive quantity greater than 0. Okay. And when you take the divergence of this second vector, divergence of v, so in this case the x component of v is minus x and y component of v is minus y. So first we have to take the difference x component of v with respect to x, that will give you minus 1, and then we have to take the differentiation of y component of v with respect to y, and we have y component of v is minus y, that will also give you minus 1. So in this case it will be minus 2, which is less than 0, less than 0. And third vector for c, if we calculate the divergence, what we'll get here? It's independent of x and y, so in this case it will give us 0. Okay, 0. So now look at this 3 vector field. First we have, let's say, a vector. We have calculated the divergence of this a vector. We have noticed that the divergence of a vector is positive, and if we take a look on the nature of this vector field, it should look like how it's look like. It's look like it's diverging from a source. There is something source at this point, and in this region vector field actually diverging. Diverging. And from second vector, where the divergence of v is negative, and if you take a look on the vector field, how it will look like? It will look like the vector field is converging at the origin. Converging at the origin. However, on the third vector field, when we take the divergence of this c, what we have noticed here, we have seen that the divergence of c is 0. Divergence of vector c is 0. And if you take the take a look on the nature of this vector field, in this case you can see here this vector field neither converge or not diverge. Okay. So from here what we can understand? We can understand that if the divergence of a vector field is greater than 0, then it will give this kind of nature. So it will look like that this vector field is diverged from certain from region, source region. And if the divergence of a vector field is negative, then it will be look like this. So what we can understand here, it will be converge to a sink region. And if the divergence of a vector field is 0, then this type of vector will neither diverge or not converge to a sink region. So let me write one by one first. So if divergence is greater than 0, what we can understand here, this vector is spreading out, or you can say diverging from a source region When the divergence of a vector field is less than 0, it will give you this kind of nature. So what we can write here, we can write here that if the divergence of a vector field is negative, then we can say this vector field, this vector is converging into a sink region, and when the divergence of vector field is 0, so this type of vector will neither converge or nor diverge. So what we can write here, this vector is neither diverging nor converging into a sink. Okay, sink region. So what we have noticed here, we have learned how to define the divergence of a vector in rectangular coordinate system, and also we have noticed that when we take the divergence of a vector field, depending upon result, if we get the positive value of the divergence, then this vector field will look diverged to a source. If the divergence of a vector quantity is negative, then it will looks converge to a point source, converge to a sink region. And if the vector field is neither, if vector field is a divergence of a vector field is 0, so this type of vector field will neither converge or diverge or nor converge to a sink. Okay. Similarly, also we have to learn how to write curl of a vector field and what are the physical meaning of curl. So write here curl of a vector. So for that, first again we'll just like divergence, first we'll define how to write curl, definition of curl, and then we'll try to understand what are the physical meaning of curl. So for that, consider a certain region, let's say R, and in this region consider a vector which is function of x, y, and z. Which is function of x, y, and z. So now what we have to do, first we'll write the definition of curl, and then we'll try to understand what is the physical meaning of curl. So to write the definition, let's write here, if A, which is function of x, y, z, represent a vector quantity in the region R, and it is differentiable at each point in this region. Then curl of A is defined as curl of A is equals to, we have to calculate this determinant. Okay, so if we solve this determinant, that will give us the value of curl of a vector. So in this determinant, in first row, write I cap, j cap, k cap. In second row, write del by del x, del by del y, and del by del z. And then in third row, write the x component of vector, y component of this vector, and then z component of this vector. So if we solve this determinant, then we'll get the value of curl of this vector A. Okay, so this is the definition of curl any vector in rectangular coordinate system. So if we know the vector quantity, any vector quantity A in rectangular coordinate system, then we can put the value of x component here, y component here, and z component here. And then if we solve this determinant, we'll get the value of curl of that vector. So this is the way how we can define the curl of a vector quantity in rectangular coordinate system. Rectangular coordinate system. Now what we have to learn here, what are the physical meaning of curl, or we can say what does it represent. What does it represent? What does it represent means, what if we take the curl of a vector quantity, what that curl actually represent. So just like divergence, as we have noticed here, we take the divergence of a vector quantity and give some nature of the vector field. If it is greater than 0, then it will be diverge from a source region, and if it is less than 0, then it will converge to a source region. And if it is divergence of this vector is 0, then it will neither converge or nor diverge. Same way, if we take the curl of a vector quantity, from there also we'll get some nature of this vector quantity. Curl also give us some nature of the vector quantity. So for that, let me just write a vector here. Let's say a vector write in this way, xi cap, yj cap, and consider another vector v vector. Let's write this way. Let's say minus y I cap plus x j cap. Okay, so we have considered two vector, a vector and b vector in xy plane, and then let's draw this vector first in xy plane. Let's say this is y-axis, this is x-axis, and in this case, again, this is y-axis, and this is x-axis. Now let's draw this vector quantity on this xy plane. So for first, already we have drawn this vector here also, a equals to x I cap, y j cap. So it will be look like the same, this vector field. So we can draw like this. At origin it will be 0. Then on x-axis it will look like this. On y-axis it will look like this. Negative x-axis it will look like this. Negative y-axis look like this. On xy plane, on the first quadrant it will be look like this. In second quadrant it will be look like this, and on third quadrant look like this, and in fourth quadrant will look like this. Okay, and then if we want to do the second vector in the xy plane, again on the x-axis, on the at the origin x and y both are 0, so it will give a null vector. And then if we want to draw in positive x-axis, so on the x-axis y will be 0, and if we put the value of x equals to 1, 2, 3, what will get? B will get j cap, 2 j cap, 3 j cap. That's mean this is 1 j cap. When x equals to 2, it will be 2 j cap. When x equals to 3, it will be 3 j cap. And if you put x equals to 4, then it will be 4 j cap. Okay. Now, if we put the value of y on the x-axis, so on the x-axis, x will be 0, positive x-axis, positive y-axis, x will be 0, and y will be plus 1, plus 2, plus 3. So when we put value of y plus 1, plus 2, plus 3, it will give you b vector equals to minus I cap, minus 2 I cap, minus 3 I cap, minus 3 I cap, and minus 4 I cap. So minus I cap means it will be negative x direction, and as we increase the value, the length will also increase. Okay, and then we want to draw this vector on the negative x-axis. So again on the negative x-axis, y will be 0 and x will be minus 1, minus 2, minus 3. So what we'll get here? We'll get here minus j cap, minus 2 j cap, minus 3 j cap. So on the x-axis, directions of vector will be negative y direction, and magnitude will slowly increase like this. Okay, and on the negative y-axis, again we'll put y equals to minus 1, minus 2, minus 3, and x will be 0. So when we put minus 1, minus 2, minus 3, what we'll get here? Already there is a negative sign, so it will give you plus I cap, plus 2 I cap, plus 3 I cap. So here electric field will be along the direction of positive x-axis, and magnitude will also increase like this. Okay. So here we have drawn few discrete points, the value of this vector, a few discrete points, and if we draw vector quantity at every point, this will give you like this. So it will look like that vector quantity actually rotate around this z-axis. Z-axis like this way. So now we take the curl of this vector quantity A. What we'll get here? Curl of A. We know how to calculate this curl. For that, we have to use this definition. So for that, what we have to do here? Write here I cap, j cap, k cap, and then we'll write del by del x, del by del y, and del by del z. And after then we have to write x component. So in this case, x component is x, y component is y, and z component is 0. So now if you solve this determinant, what we'll get? So if we want say we want to calculate I component, then what we'll get? We'll get first we have to differentiate this y with respect to 0. Sorry, 0 with respect to y, that will give you 0, and then y with respect to z, that will also give you 0. So 0. And then if we want to find out z cap, for that what we have to do? Again, first we have to calculate, we have to differentiate x with respect to z, and then we'll differentiate 0 with respect to x, that will also give us 0. And for k component, we have to differentiate y with respect to x and x with respect to y. So all component will be 0. So curl of this vector will be 0. And same definition if we use here, curl of b, so what we'll get here? We'll get I cap, j cap, k cap, and then del by del x, del by del y, del by del z, and now x component is minus y, and y component is x, and z component is 0. Z component 0. So in this case, if you calculate I component, that will give you 0, j component give you 0, but if you calculate k component, what will get? We have to differentiate this x with respect to x, that will give you 1, and then we have to put a minus sign, and then we have to differentiate minus y with respect to y, that will give you minus y. Already we have a minus sign before, so finally it will give you 2 k cap. Okay, 2 k cap. Okay. So now take a look on this vector. So we have considered two vector, a vector and b vector, where this a vector looks like it is diverged from a point source. It is not rotating about any axis. But if we take a look on the b vector field, what we can see here, this vector actually this vector is rotating around the z-axis, around the z-axis. And then when we take the curl of this vector quantity, what we have noticed that for first vector, we get curl of this vector field is 0, but for the second vector we get curl non-zero. So you can write this is non-zero. So from here what we can write, that if the curl of a vector quantity is non-zero, if we calculate a vector curl of a vector and if we get a non-zero, then we can say that this vector field will rotate around some axis. This vector field will rotate around some axis, some arbitrary axis. So this type of vector is called rotational vector. So this vector field is rotating around z-axis. In this case, you can say a k cap direction. Rotational direction is along k cap. That means it will be rotated around z-axis. And this type of vector is usually called rotational vector because it is rotating around some axis. So it is also called rotational vector. Rotational vector. And we take the curl of a vector quantity, and if we get 0, then this type of vector will not rotate about any axis. This will not rotate about any axis. So what we can say, this vector does not rotate around any axis, and this type of vector is called irrotational vector. Irrotational vector. Irrotational vector. So from 12th class concept, we can say if we have electrostatic field, curl of electrostatic field always give us 0. That's mean electrostatic field is rotational or irrotational? Electrostatic field is irrotational because curl of electric field is 0. However, if we consider a magnetic field, then generally the curl of V is give you mu naught J, that is current density. So magnetic field of curl of magnetic field will be non-zero. So magnetic field actually a rotational vector. Rotational vector. Okay, so that's it. If the curl of a vector is 0, then this will give you irrotational vector. We can say this vector is irrotational vector. This type of vector will not rotate about any axis. If the curl of a vector field is non-zero, then we can say that this vector field will rotate about around some axis, and this type of vector is called rotational vector. Okay, so now we know how to write the gradient of a scalar field in rectangular coordinate system and what does it physical meaning, and also we know how to write divergence and curl and what is their physical meaning. So now what we have to do, once we know the physical meaning of curl, divergence, gradient, and now if we change the rectangular coordinate by spherical polar coordinate or cylindrical coordinate, the physical meaning of curl, divergence, gradient will not change. Only the thing is we have to write this definition in a different way. So for that, I am writing a general definition here, and using this definition you can write the gradient, curl, divergence in any rectangular coordinate system, any coordinate system. So for that, let me draw a table first. So right here, coordinate system. Coordinate system. And then we'll write variable associated with each coordinate system and the coefficient of elementary length associated with different variable. So right here, rectangular coordinate system, then spherical polar coordinate system, and then cylindrical coordinate system. Okay. And this in general we write is in this way. Let's say u1, u2, u3, and h1. One more thing we have to also define. Let me just divide it. H1, H2, H3, and then E1 cap, E2 cap, and E3 cap. Okay. So what are these U1, U2, U3? These are the variable associated with each coordinate system. So in rectangular coordinate system, variables are x, y, and z. So in this case, we'll write x, y, z. In cylindrical coordinate system, spherical polar coordinate system, distance from the center that we have defined as r, we have represented by r. Then we have also defined the angle between r and positive z axis by theta, and the projection of r on the xy plane and the positive x-axis, the angle between projection on the xy plane and the positive x-axis, that is phi. And then in cylindrical coordinate system, perpendicular distance from the axis rho, the angle between plane and the positive x-axis we have defined by phi, and then perpendicular distance from the xy plane z. Okay. Now what is h1, h2, h3? You remember that when we write this elementary length in rectangular coordinate system, what we have written there, dx I cap, dy j cap, and then dz k cap. So here this h1 is the coefficient of this dx. So x component of elementary length is dx, and the coefficient of dx is in this case 1. So in rectangular system it will be 1. Similarly, coefficient of dy is also 1, and coefficient of dz is also 1. And this e1, e2, e3, they are the associated unit vector. Unit vector associated with each variable in this particular coordinate system. So in rectangular coordinate system, these unit vectors are I cap, j cap, k cap. So I cap, j cap, k cap. Then in spherical polar coordinate system, again let me write the elementary length here. We have written that dr r cap, and then r d theta, theta cap, plus r sine theta, d phi, phi cap. So if we consider elementary length along r cap, that is dr, so what will be the coefficient of dr? 1. Elementary length along theta is r d theta, so what is the coefficient of d theta? R. And elementary length along phi is r sine theta d phi, so what is the coefficient of d phi? Is r sine theta, r sine theta. And then unit vector r cap, theta cap, phi cap. And same way in cylindrical coordinate system, we have written elementary length dl is equals to d rho, rho cap, and then rho d phi, phi cap, and dz, z cap. So here the coefficient of d rho is 1, coefficient of d phi is rho, and coefficient of dz again 1, and unit vector rho cap, phi cap, z cap. Rho cap, phi cap, z cap. Okay. So I hope you understood how I have written this this table. I have written this table. Rectangular coordinate system, and these are the coordinate system, and these are the variables, and then h1, h2, h3, they are the coefficient of elementary length, and e1, e2, e3 cap, they are the unit vector associated with each variable. Okay. So once you know this table, and then using this general definition, you can write the gradient of a scalar function in any coordinate system. Divergence, curl, you can write in any coordinate system. So if phi is given any arbitrary coordinate system, let's say spherical polar coordinate system or any coordinate system, then we can define grad phi in this way, in terms of h1 will write 1 by h1, and then del phi by del e1, e1 cap, plus 1 by h2 del phi by del u2 e2 cap plus 1 by h3 del phi by del u3 e3 cap. Okay, good. So this is the general definitions of grad phi. So that's mean if the phi is given in rectangular coordinate system, then what you have to do, you have to replace this u1 u2 u3 by xyz and h1 h2 h3. In this case, from this table you can see here h1 h2 h3 all are 1, and e1 cap e2 cap e3 cap you have to replace by I cap j cap k cap. Okay, and if this phi is given in spherical polar coordinate system, if the scalar function in term given in terms of spherical polar coordinate system, let's say function of r theta phi, later we will see if the potential associated with the dipole, if we want to calculate potential associated with the dipole, usually we use a spherical polar coordinate system. So in that case, if we want to calculate the electric field from this potential of the dipole, what we have to do, we have to take the gradient of this potential. So when you take the gradient of this potential, you have to write in terms of spherical polar coordinate system. So if you want to write the spherical polar coordinate system, then what you have to do, you have to replace by this h1 h2 h3, in this case 1 r sine theta, and then you have to replace this u1 u2 u3 by r theta and phi, and e1 cap e2 cap e3 cap you have to replace by r cap theta cap phi cap. Same way in cylindrical coordinate system. Okay, and then if you want to define the divergence of vector quantity, so the general definitions we can write in this way: 1 by h1 h2 h3, and then what we have to do, we have to differentiate with respect to u1, and we have to multiply here h2 h3 and then first component of this vector. That's mean if this vector is given in a rectangular coordinate system, then it will be x component plus del by del u2. Now we have to multiply with h1 and h3 and the second component of vector, plus we have to differentiate with respect to u3, and that will give you, and then we have to multiply here h1 h2 and third component of this vector quantity. Okay, so using these definitions you can define the divergence of this vector A in any coordinate system, either in rectangular coordinate system or in spherical polar coordinate system or in cylindrical coordinate system. So which coordinate you have to use, that will be depends on questions paper. So if A is given in rectangular coordinate system, then you have to put the value of h1 h2 h3 u1 u2 u3 in terms of rectangular coordinate system x y z. If this A is given in spherical polar coordinate system, then you have to put this h1 h2 h3 and u1 u2 u3 according to spherical polar coordinate system. And if it is given in cylindrical coordinate system, then you have to replace this h1 h2 h3 or u1 u2 u3 in terms of spherical cylindrical coordinate system. Okay, and third is curl of a vector field. Curl of a vector field. So for that, what we have to do, first we have to divide here 1 by h1 h2 h3, and then have to solve this determinant. The first row will be like this: h1 e1 cap, h2 e2 cap, and h3 e3 cap, and then del by del u1, del by del u2, and del by del u3, and then again h1 into first component of vector, h2 into second component of vector, and h3 into third component of the them. Okay, but this a1, a2, a3, okay, first component, second component, third component means if this a is given in rectangular coordinate system, then it will be a x component, a2 will be the y component, and a3 will be the z component. If this a vector is given in spherical polar coordinate system, then this a1 will be r component, a2 will be theta component, and a3 will be phi component. And if it is given in cylindrical coordinate system, then this will be rho component, this will be phi component, this will be z component. Okay, so using this definition, we can define the divergence and curl and gradient of a scalar function in different coordinate system. So yeah, so this will be enough to understand the electrostatic phenomena or electrodynamics phenomena related to the gradient curl divergence. So what we have learned today, how to write gradient divergence curl in any coordinate system, and what is their physical meaning. What is their physical meaning? In next class, we'll talk about two theorem, Green's theorem and divergence theorem, and then we'll talk about one special function, that is a Dirac delta function, and how this Dirac delta function, how using this Dirac delta function, how we can represent a point charge as a continuous charge, let's say linear charge or surface charge or volume charge. So we'll learn that thing in next class. Sure. Thank you for watching. We'll see you in the next video.